welcome to lesson 21 of the course Industrial Automation and Control. In this lesson, we are going to learn a structured design approach to sequence control. So far we have mainly seen the programming constructs, have seen small program segments, timers, counters. In this lesson, for the first time, we will see that given a practical problem, how to study the problem, what are the steps that you go through to finally arrive at an RLL program. So, and this will be followed using a very systematic approach, because as I have already told you that industrial control applications are very critical in the sense that if you have programming errors in them, they can be very expensive in terms of money or in terms of even can cost human lives, etc. So, it is always good to have a very systematic design process by which you can decompose a problem and then finally arrive at a solution. So, we will look at the instruction objectives. The instruction or objectives of this lesson are firstly to be able to model simple sequence control applications using state machines. State machine is actually a formal method, and we advocate the use of formal methods because English can be very ambiguous, sometimes contradictory also. So, we have to model it using methods which are unambiguous, consistent, do not contain contradictions, and are also easy to understand and develop. Then from these formal models, we have to develop RLL programs for such applications, and for doing this there are certain, apart from the RLL programs, there are some modern programming constructs which are being made available. One of them is the SFC, or the sequential function chart. So, we will take a look at that and also understand some of its advantages. So, that is these are the instructional objectives of this lesson. So, now let us go through the steps in basic broad steps in sequence control design. So, first step is to study the system behavior. This is a very critical step, and most of the errors that happen in any programming exercise, not only this kind of industrial automation programming, any programming, mainly arises from the fact that the programmer or the developer did not understand the system well. So, this is a very important step, and one must first of all identify inputs to the system, that is the programmable controller program, what inputs it will take. Inputs can come from either from sensors in the field, or it comes from operator interface, which I call the MMI, or the man machine interface. So, somebody presses a push button, that is an operator input, right. On the other hand, some limit switch is made, that is a sensor input. Similarly, identify the outputs. So, switch on motor. So, motor is an actuator, that is a kind of output. There is another kind of output, for example, switch on some indicator or some lamp, that would be an output which again goes to the MMI or the man machine interface. So, we have to first identify these. Then study the sequence of actions and events under the various operational modes. This is the main task. You have to very carefully understand what is going to happen and what will happen after what, at what time intervals, etc. Then one thing that must be very clearly remembered is that when you are developing an industrial automation program, one not only has to remember, not only has to design for normal behavior, but one must to some extent at least take into account the possible failures that can occur. Otherwise, a system that behaves well under normal behavior can behave in a very nasty manner if some simple element of the system like a sensor fails, right. Then even apart from the automated behavior, one has to examine the requirements that exist for number one, manual control. Manual control is very important, because for finally if the automation equipment fails, it should be able to operate the system using manual control, right, maybe right on the field, while the automated control may be actually working quite a distance away from the actual equipment. It may be housed in some control room. On the other hand, the manual controls may be near the equipment at the field. So, the possibility of including such manual controls must be examined. Whether some additional sensors are required, some sensors may be there, but to achieve a kind of functionality some other sensors may be needed. Indicators, alarms, and as well as operational efficiency or safety. These are the factors which must be considered to finally arrive at the functionality. One must always remember that the customer may not always be able to express his or her needs, and a good automation engineer should be able to supplement it with his own experience in such cases. So, having done that, the next step is to convert. Generally these things are captured manually and using a linguistic description, something like something like English statement. So you talk to customers, talk to engineers on the field and get their requirements. But this is very dangerous to use for program development. So we have to convert this linguistic description into formal process models, and in fact a lot of inconsistencies which are there, ambiguities which are there in the linguistic description actually surface at this time. Even for during the process of transforming it into a formal process model, one may initially use intermediate forms like like flow charts, for example. Okay. Then finally it is prescribed that one should be able to convert it to a formal mathematical framework, something like let us say a finite state machine, which we will be using here. After up to this the operations are manual. Having done that, then one has to go for design of the sequence control logic based on the formal model, and then finally one has to implement the control logic in the form of an RLL program, and it is preferable that these steps, especially the step D, is made as much as possible automatic, because this is a step which can be done in an automated manner once B and C have been carried out, and for large programs it is always preferable to go for automated programming, because that will always lead to error free programs provided your specifications were correct. So we come back to our old stamping process example which we have seen in earlier lectures. So here is a stamping process, we know this process. So we have made some addition to its functionality to be able to explain certain features of a system and make it more complete. So basic principle is the same, that there is a piston and there are two solenoids, hydraulically driven piston which goes up and down and makes stampings. Okay. So if we now try to write its list of actions, try to create a linguistic description of the process operation, it will look something like this. So in step A, it says that if the auto push button is pressed, so that is an operator input, it turns powers and lights on. So there is possibly a switch, one or more switches, but we will consider it to be one, which will turn the power and the light on the moment the auto button is pressed. When a part is detected, the thing to be stamped, when it is detected, when it is placed at the proper place and detected, so there has to be a part sensor. The press ram, the thing that will, the heavy piece which will move and make a stamping, it advances down and it will stop once it makes the bottom limit switch. So that is again a sensor, and you must have actuators to make the ram move down. Then the press then retracts up to the top limit switch and stops. So it makes a stamping and stops. All right. On the other hand, due to some reason, the operator may like to abort a stamping operation. So there is a stop push button provided to the operator, and a stop push button stops the press only when it is going down. When it is going up, it has no effect, because anyway that is not going to cause any problem. If the stop push button has been pressed, it means that something abnormal might have happened. So the reset push button must be pressed before the auto push button can be pressed for the next cycle of operation. So once you have pressed stop, you have to press reset. It's a kind of acknowledgement that the emergency has gone away and the automated operation can resume. Finally, after retracting after retracting and then going up, the press waits till the part is removed and the next part is detected. So, till the part will be removed and then after that when the next part will be detected, again the RAM will start coming down. So, this is the English behavior of the system. Okay. So, now let us try to convert it to an unambiguous mathematical description. So, first step, as I said, is to get the process inputs and outputs. So, what are the process? So, here are the process inputs and outputs. So, as inputs we have part sensors, which gives which generates two kinds of events. One is part placed, another is part removed. Then there are three kinds of push button, the auto push button, the stop push button and the reset push button. These three are operator inputs. Then there are the two limit switch sensors, bottom limit switch and top limit switch. For outputs we have four outputs. We have an up solenoid which moves the RAM up, we have a down solenoid which moves it down, we have the power light switch and we have a part holder which holds the parts while it is being stamped. So, these are our outputs. Now, we develop a state machine. So, let us try to interpret this diagram. So, what is happening in this diagram is that let me select my pen. So, what is happening is that you see these squares are the states. We are possibly familiar with state machine. So, a state machine is like a graph which consists of a set of states, these squares are the states, and a set of transitions. For example, this is a transition, this is not a good color, go back to white. So, this is a transition and this is a state. So, this is a transition and this is a state. So, what the system does is that the system actually during its life cycle or during its activity, the system actually moves from states to states through transitions. So, it actually spends time, most of the time, in the states, and transitions are generally assumed to be momentary, that is, it is assumed that insignificant amount of time is required to change states. So, you see that it says that initially when you have double square, it means that that is the initial state. So, if initially if the auto push button is pressed, this is a transition A which gets activated, which will take place and take the system from state 1 to state 2 if the auto push button is pressed. So, this is the transition condition. You can have much more complicated conditions, in this case we have very simple conditions. And then if this transition occurs, then this system comes to state 2. In state 2 again, if this transition B takes place, whose condition is part placed, it will come to state 3. So, in this way, depending on how the sensors are bringing in signals from the field, the various transitions will be enabled and the system will hop from state to state. That is the behavior of the system. On the other hand, these green rectangles indicate that at each state, which are the outputs which are on. For example, you can see that in state 1 nothing is on, none of the outputs are exercised, while in state 2 the power and lights are on. In state 3 the down solenoid is on, actually this is the state when the solenoid is coming down. So, you see that this is the initial state, here the system is switching on the power and the light and possibly waiting for part place signal to come. So, it might spend some time here, then it is coming down, so it takes time there. Then from here it could either go this way or go this way, and depending on which one of this have come. So, it may so happen that the bottom limit switch, if the stop push button has not been pressed, then eventually it will the bottom limit switch signal will come and then it will come to step 4, in which it will activate these outputs. On the other hand, if before the bottom limit switch is pressed, if the stop push button is pressed, then it will come to this state where it will simply stop and put the power and light off. So, you see, so this is the way, using a graph of nodes and edges, we can describe the behavior of the system unambiguously. So, now, so this is what we know, what we call the state transition diagram, and these are the outputs which are exercised at different and that is actually also in captured in what is known as an output table. So, the output table says that among the four outputs that we have, namely power, light, part hold, power light switch, part hold, up solenoid and down solenoid, which are, what are their status, whether they are on or off in the various states. So, there are 6 states and there are 4 outputs. So, it says that the power light switch stays on in state 2, 3, 4 and 6, right, while the part hold stays on only during 3 and 4, up solenoid is 1 during 4 and down solenoid is 1 during 3. Having done that, we can start developing our, so you see, we have seen that as the system moves on, the various state logics and transition logics are alternately computed. So, first there is a state in which some state logic will be satisfied, depending on that outputs will be exercised. After that, at some time some transition logic will get satisfied. So, now the system will come to a different state. So, the previous state logic is going to be falsified and the new state logic will now become true, and then based on that the corresponding outputs will get exercised. So, this we have to now capture in a relay ladder logic program, right. So, we will organize our program into 3 different blocks. The first block, the first block will contain, so maybe I will choose this pen now. So, the relay ladder logic will consist of 3 different blocks. Okay. The first block will contain the transitions. This is multiple rungs. Then the state block and finally the output block. So, we will now describe these 3 blocks in the case of this example. So, let us first see the transition logic. For example, what does it say? It says that when will transition A logic will be satisfied? The transition A logic, if you recall, brings the system from state 1 to state 2. So, if you wanted to see that, we could go back just for once. So, you see here, transition A takes the system from state 1 to state 2, transition B takes it from state 2 to state 3, transition C and D are in parallel, it could take state 3 to either 4 or 5. So, let us remember this and then go ahead. So, it says that if the system is in state 1, if it is in state 1, that depends on the state logic, then the corresponding to every transition we have an output coil, and corresponding to every state we have output coils. So, this is actually an auxiliary contact corresponding to the output coil called state 1. So, it is an abstract variable actually. So, it says that if the system is in state 1, then this contact will be made, and at that point of time, if the auto push button signal comes, then transition A will get enabled. So, it will be on, right. So, if we have modeled our system well, then at a time only one transition will get on, right. If we do not consider concurrency, then at a time only one transition will get on. Now, what will happen? Now, in the next stage, So, now transition A becomes on and state 1 was already on. So, at this point of time we come to the state logic. So, now let us see what happens in the state logic. In the state logic, see, state 1 was on, right. Now, because state 1 was on and because auto push button was pressed, transition A became on. So, the computation came from the transition logic to the state logic. So, what happens is that it found state 1 is on. So, what happened is that it found that the transition A is on. At this point of time it found this transition on, because transition logic has been already evaluated and it has been found to be true. So, therefore, this auxiliary contact will be closed. So, therefore, now state 2 will be on. Now, once state 2 is on, two things happen. Firstly, you see, in the next, because state 2 is on, this will be on, this contact will be on, and this contact will now be off. So, in the next cycle, in the next scan cycle, when these rungs will be evaluated, this will go off, and because and transition A will, because see this will go off and this will go off. Therefore, because transition A will go off, so therefore state 2 this can go off, it does not matter because this is on. So, therefore, this will stay on. So, therefore, it says that now the system is in state 2, right. Now, when in this way again, when state 2 is on, at that time in the next cycle some other transition will become enabled depending on what sensors, what sensor signals are coming. So, similarly it will turn out, for example, in state 3, now at some time transition B will take place. Transition B means that transition B is, let us see transition B. So, transition B is part placed, correct. So, when the part will be placed, then if that part placed signal comes, then what will happen is the transition B will be on and these are not yet enabled. So, therefore, state 3 will be on, right. On the other hand, while state 3 is on, if either transition C or transition D occurs, transition D is due to the stop push button being pressed and transition C is due to the bottom limit switch being made. If any one of these occurs, then it will no longer be in state 3, but it will go to either transition state 4. If transition C occurs, state 3 will be falsified and state 4 will become on. On the other hand, if transition D occurs, then this will be falsified and state 5, which is not shown here, will become on. So, you see that mechanically, once we have developed the state graph, we can simply mechanically describe its behavior. So, corresponding to every transition we are going to have one rung, corresponding to every state we are going to have one rung, and as I have described, we are going to put the enabling logics. So, we are going to say just from the graph that if when the system is at state 1, if auto push button is pressed, it will go to state 2. Simple, this logic which is given from the graph will take every transition and will write the corresponding logic in the transition logic. Similarly, we will say that if transition X has been enabled, then it will reach this state. So, we can do it from the graph mechanically, just one by one. This writing can be actually written by a program itself. So, one need not really think too much about the logic, one should think about the logic while he is drawing the diagram. After that, the programming becomes automated. This is very useful. Okay. So, now next we will have the output coil, output logic. Output logic is very simple, very simple, especially in this case. So, the output logic says that if you are in state 2, then power light switch should be on, as we have given in our output table. So, only thing is that look here, that we have also added some manual switch. It can be sometimes we may need to check, we may need to do things manually also. So, the power light switch will be on, here we have put a manual switch. So, if the PLC is running, then if you press the manual switch, then also power light switch may be made on. Similarly, we can have a manual down push button. So, we can, this is just to demonstrate that you can put additional logic to include manual operation of the system. So, in this, so otherwise this program simply says that while you are in state 3, down solenoid will have to be activated, very simple. Compare this with the kind of programs that we had written earlier. In fact, for this process itself we had written some programs. So, there we did not have any concept of states and transitions, we were directly trying to write outputs in the form of inputs. Now, the problem with this kind of problems is that they are here systems generally have memory, that is why you need the concept of states. It is not that if you get a certain kind of inputs, you will have to produce certain kinds of outputs. It depends on which state the system is in. So, the concept of state is very important, and well, you can bring it down in possibly in certain cases using some temporary variables, but the kind of here you see if you look at this program says it is very complicated logic, and I am not even 100% sure, it is very difficult to be 100% sure whether this logic is foolproof. It says that if the auto mode, by the way, this auto mode is actually a it's an auxiliary contact corresponding to some logical variable which you can set by a simple rung, that if it is auto PB, and then you have an auto mode coil, and then you have this is auto PB, and here you can have auto mode. So, you can have a auto mode coil, and this will be an auto mode auxiliary switch, so that the PB can be released. So, this is a sort of a persistent input. So, if this auto mode is on, so it says that this everything will work only if the auto mode is on, and then if the bottom limit switch is made and the down solenoid is not on, then the up solenoid will be energized. Similarly, and once the up solenoid is energized, it will remain energized until the top limit switch is looks okay, but one is never sure, and especially when problems will have 200 states, then it will be impossible to write such direct programs. Chances will be very high that if somebody wants to write it, he will make mistakes.